We keep studying the advanced compiler course to become rich, famous, and all that stuff. And the last time we wrote a few simple functions which takes intermediate language representation of the program and split it into blocks, and after that building a control flow graph out of those blocks. It's not a huge deal, I would say, but some practice. So we got our hands dirty with Guile itself and with scheme implementation of those functions. Today we will start lesson 3, which makes that we will be doing some optimizations. I'm not sure if we do all the tasks, but at least we will do some of the coding. Also, in the meantime, yesterday I made a few packages for our project. One of them is gigs package and channels package, which allows to access gigs API from our project directly. And the second one is Dino package, which allows us to run TypeScript code that we have in Guile repositories. And I think let's comment this stuff so I can push it. Channels and then packages and Base interactive. How to trigger a fix-up? Okay. Stuff to comment function. Okay, I think we are ready to push. I made this repo on the GitHub, so you can access it right here. It doesn't have any readme for now. Okay, let's start our timer and start watching the election.
Today we're going to dive in and write our first compiler optimization. We're going to start with a few simple optimizations around the theme of dead code elimination. But before we do that, I want to give some framing for different kinds of optimizations we'll study in 6120. The difference is between how we deal with control flow in the program. So you'll remember from last time that we started drawing control flow graphs, that is, breaking up programs from just sequences of instructions to these graphs indicating basic blocks and how control transfers between the basic blocks. So here's a sample CFG. At a very high level, in this class, we're going to categorize optimizations into 3 different categories: local optimizations, work within a single basic block. That means they don't have to deal with control flow. They just have to deal with the ordering of instructions in a sort of linear scan. Global optimizations work on an entire function. This means they have to deal with control flow. And as we will demonstrate in this video and the next one, dealing with control flow makes optimizations, typically speaking, much more complicated. Finally, there's a third category of optimizations we'll get to later in this semester, which has to deal with multiple functions. And those things are called interprocedural optimizations. Local and global optimizations can also be called intraprocedural, especially if you spell it correctly. But the words interprocedural and intraprocedural sound so incredibly similar to each other that it's more useful to say local and global when you're referring to things that work within the scope of a single function. But one thing to remember is that when you say global, you might think that, well, global, that means the entire program. That's not what people mean. By global optimizations, people mean global with respect to a single function. Interprocedural optimizations are a even fancier level that goes beyond global and looks at calls from one function to another. So if this basic block, for example, had a call to this function, we'd have to sort of reason about those calls. When we're doing global optimization, we don't even reason about calls. We're going to start out by thinking locally, that is within a single basic block. We will also see some optimizations that apply globally to the entire function in a kind of trivial way first. And then later, in a few more lessons, we're going to see more sophisticated ways to reason globally, that is to reason about control flow. And I hope that one of the things you'll take away from this video is understanding what the fundamental shift in thinking is that has to happen when you transition from thinking within a single basic block to thinking about an entire CFG. Let's start out by looking at a Brill program that's possible to optimize. We're going to start out by thinking about dead code elimination, which is a simple kind of optimization that removes code that can't possibly have an effect on the output, thereby making the program faster. I hope you're getting more familiar with Brill programs and this instruction-based syntax and the semantics of the various instructions. So I hope you're able to understand this simple program that just has a couple of adds of constants. And my question to you is, what should we do to this program in order to make it faster? Where is the optimization opportunity? Of course, it's not too hard to see. There is this one.
Yeah, we just can remove the statement that doesn't affect any consequent statements.
Instruction here, this assignment to the variable c, that is never used anywhere in the program. And so it's possible to delete this instruction and to get an equivalent program that runs faster, that is, it uses one less instruction when executing, but does exactly the same thing. So the next question I have for you is, what is the general principle, that is, can you phrase it in a sentence, for what opportunities exist, like this one, for optimizing Brill programs?
How we formally understand that this line is not necessary and optional and we can remove it. Not even optional, but redundant. I think here we need to understand where our side effect happens or return value happens. There are like two kind of things we are looking for. And in this example, we don't have a return statement, so my function doesn't return anything. So we look for side effects. And the only side effect we can find here is print, because print like affects external world by sending some output to stdout or somewhere else. So we found out that we have a side effect on this line. And this side effect requires one argument, and from this point we can find all the code that affects this one argument. We go to the place where it's defined and see that the value of the d variable depends on a and b, and that means that we can add a and b to the list of things that affects the resulting value of this side effect. So after that we find those two lines and also mark them as useful and affecting the final result, and basically we are finished. This is kind of continuous process when we just start marking things one by one, where they a part of dependency graph of this value. And like when we marked all the dependencies of this value, we found all the instructions that we want to keep, and the rest probably unnecessary.
If we were to implement an optimization, what would we be looking for? Try to phrase that in a sentence. Try actually writing it down. Here's how I would phrase it. We can delete any instruction that assigns to a variable that is never used as an argument anywhere in the function, as long as that instruction has no side effects. By side effects, I just mean that we shouldn't eliminate instructions that don't seem to assign to a variable, and yet they have an effect on the outside world. For example, Brill has a print instruction. You can say like print C, for example, and it shouldn't be penalized for the fact that it doesn't assign to a variable, and therefore it seems to be dead because it doesn't produce any values used elsewhere. The criterion that we can use to do some dead code elimination is just to eliminate every instruction that has this pure semantics that all it does is assign to a variable, and that variable is never used by any instruction everywhere in the entire program. Therefore, this is a global property. We've come up with the framework, at least, for a global optimization that needs to look at the entire function. We happen to be looking at a function here that only has one basic block, but this is a global property. It's not possible to implement by looking at a single basic block. It's possible that you don't use C in this basic block, but in a larger function, for example, then you jump to another basic block that does use C. Therefore, this is a global property. To turn this into a real optimization, I would like you to now try writing the pseudocode for an optimization that carries out these instructions. That is, that analyzes a program and deletes every instruction that is dead by this definition of assigned to a variable that is never used anywhere and also not having any side effects within the instruction. Go for it. Here's my pseudocode. Works in a kind of two-pass style. There are two loops. The first loop loops over all the instructions and accumulates a big set of all the variables that are ever used anywhere in the function. The second loop goes over all the instructions a second time and looks for instructions that have a destination, and that destination is not in the used set, and it deletes those instructions. This relies on a simple property about Brill.
This is probably wrong. It's wrong because imagine we have another expression here. Instead of C just assigning a const, we assign const a result of adding B and D variable, not D, B and gamma variable, which are defined like as above the C variable. That means that our gamma variable will be used by this expression, but we still don't need those two statements because they don't affect our program anyhow. They just assign some variables that we never use later. But they will be marked as used on the first traverse of the instruction list, because gamma variable is argument for this expression. That means that when we will be eliminating that code, we will see that our instruction destination is used by this expression because C uses the value of gamma, and we want to remove gamma variable. So we will need to redo this operation multiple times to actually get rid of this instruction, which can be a bit inefficient. And in one go, we of course can't properly eliminate the dead code.
Which is that the operations that are built into the standard Brill don't have side effects if they assign to a value. That is, they can do one of two things: either they're effect operations that don't produce results, or they're value operations that don't have side effects and they only produce results. This is true of the basic Brill instructions. If we're to make more complicated instructions, we'd have to think more carefully about what the side effects of instructions are. But for example, the print statement doesn't have.
By the way, I'm not implying that he don't know about this thing. He probably shows the simplest example of dead code elimination without going too much into details. I'm just discussing the code and why this implementation doesn't remove all the unused instructions and variables from the code.
A destination field. It doesn't assign to anything. So this this instruction won't have, the print instructions won't have a destination, and therefore we will never delete those instructions. So that's a really simple implementation of our very first optimization. Great work. I want to now show you a second program that we're going to want to worry about how to optimize. As a first step, for this program, I want you to try, in your mind, running your pseudocode for dead code elimination on this program. Do that now and figure out which instructions it would delete. My implementation, at least, would delete only this instruction.
Yes, that's basically the case we were talking about a bit earlier today. This instruction will be removed, but the instruction for assigning a value to C variable won't be removed. But we actually don't need it to produce a side effect on this line, because variable D doesn't depend on variable C anyhow.
That is, this is the only instruction that's unused. And the tricky thing about this is that by thinking with your human brain, you can also realize that this instruction is also needless because it feeds into an instruction that is never used anywhere. But it doesn't meet the criterion that I set out in my pseudocode. That is, this instruction, the one that assigns to C, it doesn't have the property that it is never used in any instruction ever. So it's sort of disappointing. We know there is more opportunity to optimize here than we are giving credit for. That is, we're unable to do an optimization we'd like to do. So now I would like you to think for a second about how you can rectify this, how you can take the pseudocode that we wrote for simple dead code elimination and make it slightly more powerful to capture this case as well as the previous case. There are several ways to do it, but there's one way that's particularly easy, which is just to do the same thing multiple times. That is to run the algorithm repeatedly until it converges. And by that I just mean in pseudocode, just stick the code we had above in a while loop and run it while anything has changed about the program. This just means that we will keep running the dead code elimination, and the first trip through the while loop, we will delete this instruction, and then we'll run again, and then we'll notice that this instruction is no longer used by any instruction globally in the entire program, and we'll delete that too. This may not be the most efficient way to do this, but it is definitely the easiest. That is, all we need to do is take a single pass optimization that we've reasoned about to be at least correct, and iterate it to convergence. That is, run it until nothing changes anymore. Iterating things to convergence is going to be a cornerstone of lots of the optimizations we see in this class. I want to show you one third and final program that's going to stretch our dead code elimination abilities. Here's the program. I want you to think for a second, again, about what our algorithm so far, including iterating to convergence, will do to this program, and what opportunities that leaves on the table.
This is probably the program which will even bypass the optimization that I discussed above, the algorithm for optimizing dead code elimination, because the algorithm I was discussing will be looking for all the dependencies above this statement, and both A equal to 42 and A equal to 100 kinda seems to be affecting the value of the sprint, but in fact they are not. Can we add some heuristic here? Yeah, probably. When we will be going up the instruction list, after we see that the variable got its value, we can remove it from the list. So our side effect or return statement have arguments that it will use. For our case, it's a value. We added to the list of required arguments that we need to obtain somewhere earlier in the code. And after we reach this line, we go up the instruction list. After we reach this line, we say that okay, this line is necessary to compute the value of a, but we don't need a anymore unless somewhere in between those two statements somebody will use the value of a. So yes, that's basically will improve the code, the dead code elimination. Every time we encounter a somewhere here, like under the last definition of a, we say that we need to compute a, but we don't like count how many times it mentioned, because we need to compute it only once. So we have a set data structure where we store all the variables we need to compute before, like executing this part of the code. And after we computed the value of a, we remove the a from this set. And going further, maybe somewhere between those two definitions, we find another usage of a. We add it back to the set, so we don't remove the necessary value here. But if there is no statements between those two definitions, then the next statement will be marked as unused and will be eliminated.
If you said nothing, you're correct. The previous algorithm would do absolutely nothing to this thing, even though the opportunity for optimizing it is fairly clear. That is, this assignment to the variable a has no effect on the output of the program. The only one that matters is the second constant in the program. Clearly, there's an opportunity here to do stronger dead code elimination if we can find variables that are assigned to and then assigned to again before they're used again. I'm going to caution you, however, that this property is a little bit more subtle to implement than the previous one that had to do with just looking globally at the entire function and looking for uses of the variable. And the reason for that is because it has to do with the ordering of things. That is, the previous one really didn't care about the order of instructions. It was just saying, if you ever assign it to a variable in the entire program, entire function rather, that variable is never ever used by any other instruction, then we can be guaranteed that it's safe to delete. That's not true. That sort of like big bag of instructions model is not going to work for this type of optimization. In particular, we're going to have to think carefully about what happens globally in programs that have control flow. Let's imagine a slightly different function that has an assignment to A, and then it has another assignment to A, but in between there is a jump to a label where we print A. Of course, this code that doesn't ever get executed under this jump.
It's even trickier example. But what I would like to say here, luckily we have our code splitted into blocks, and we know that in the body of one block we don't have any jumps. This way, the local optimization for the particular block can be done the way I described here. But the global optimization, which should work between blocks, probably become a bit more complicated, but not much. You see that our block with print A will be a separate block, this block will be another block, and we have our graph, how you call it, I always forget the name. Oh, hello Alex, I always forget the name. Control flow graph. In our control flow graph, I don't know why the timer switched, because I guess I didn't spend 25 minutes on this video yet, and I didn't hear sound. Probably I accidentally pressed the button. Okay, let's come back here. In our control flow graph, we will see that from this block where the print a is used, we can reach this block only from this block, and this one will be eliminated by dead blocks elimination, and this instruction won't be eliminated because we found through the control flow graph this instruction.
That's eliminatable by a different kind of dead code elimination. But you can make this even more interesting by eliminating that possibility by changing this jump if you want to instead be a branch on some dynamic condition, say like we branch on some input we don't even get to see, to either L or to K. So we can't possibly know at compile time which of the two assignments to A, this one or this one, will actually be the one that flows to the print, that is the one that actually matters for printing stuff. In this case, I think it's fairly clear that there actually isn't really an opportunity for redundancy elimination. There may be other things we can do to this program to simplify it so we're not like assigning to A and then reassigning to it. There may be other things we can do, but it's not going to be as simple. That is, like, there's not going to be a dead code elimination opportunity here. It's as simple as just deleting an instruction. And if you wrote an optimization based on the example on the left that naively assumed that all we had to do was scan through and look for assignments that to the same variable that happened twice in a row, then we might think that we can eliminate this instruction. And that's clearly not true. Instead, in order to get this right, we would have to reason globally about the control flow of the program. That is, we would have to think in terms of the control flow graph that says that we have an A assignment here and an A assignment here, and then finally a use of A in the final block. Instead of doing that, what we're going to do at this juncture is just reason locally. That is, by restricting the reasoning to think only about these redundant instructions within a single basic block, we can avoid the entire problem of reasoning about control flow, which creates a much different kind of problem we'll solve in a future video. But for now, there's enough to be done just thinking about programs like the one on the left. That is, where there's an opportunity for reducing redundancy within a single basic block. That is, that there's a local optimization to be done that doesn't have to reason about control flow. And that property, just to state it clearly, is that we can delete instructions that assign to variables that are then reassigned later within the same basic block, just sort of later in the sequence of the instructions within the block, before they're ever used in any other instruction. So now I would like you to write down some pseudocode for how to implement that local optimization that reduces dead stores to variables within the context of a single basic block, a local dead code elimination based on overwritten variables. This will be a little bit more complicated than the previous one, so take your time and write some pseudocode now. Okay, here's my idea for how to do this.
Okay, I already mentioned how we actually approach this dead code elimination where we don't have any jumps. So, like a few minutes ago, and I won't repeat it. So let's listen what you have to say.
Algorithm. I'm interested to hear, if you want to post on Zulip, what you did differently, because I think there's a lot of different ways to do this. But here's my idea. We're going to start, of course, by doing a for loop over the instructions, but this time, instead of doing instructions in a program, we'll now loop just over the instructions in a block. My idea is to keep track of those variables at every point in the block. That is, after every instruction, we're going to keep track of those variables that have been defined but not used. That is, variables that have been assigned to, but they haven't actually been consumed yet. So these are the candidates for deletion. And if we ever see another assignment to that variable before we get to the end of the block, then we know that the previous assignment is worth deleting.
He goes the other way around. He goes from the top to the bottom and remove mark instruction as unnecessary when we find another assignment and this variable never been used between two assignments, which also make a lot of sense.
So this means that we will preserve variables that are assigned to but never used once we get to the end of the block, because we might be jumping somewhere else that's going to use those variables. And we're not going to worry about global optimization at all. But we can say that if we ever hit one of those candidates for deletion, that it's defined but not used, and we hit another definition, then we know that there's a deletion opportunity. So here's my idea. We're going to have a mapping called lastDef that keeps track of those variables that are defined but not used yet. And this is going to be a mapping from variables to instructions. So this is going to keep track of the last definition, the most recent definition, but only of variables that haven't been used yet. So in the instruction, we're going to do this in two phases. In the loop, rather, we're going to do this in two phases. We'll first check for uses, and then check for definitions. It has to go in this order because instructions can be both users and definers. That is, if you say like x equals x plus 1, for example, you're using x and then defining x again. And we don't want to consider x dead just because we're assigned to x, because we're also reading the previous value of x. In any case, we need to check for uses first. So the way this will work is that we'll look at whether the instruction has any arguments. And if so, we will take those things out of our last defs. Remember that this last def thing, I'll do minus equal to say we'll take out all those variables that are now being used. Last def is meant to keep track of all the variables that have been defined but not used yet. And we're encountering a use of the variable for everything in inster.args. So we're going to take it out of this candidate for deletion. Okay. The next thing we need to do is to check for definitions. And there's two things we need to do definitions. We need to put things into the candidates for deletion, and we need to mark things, and we need to actually delete some instructions if we notice an opportunity for redundancy. So the way that works in Brill is that instructions have a dest field, which is the variable they assigned to. What we're going to need to do is check whether we have any candidates for deletion, that is things that have been assigned to but not used that we're now reassigning to. So we can say, if this destination, that is the variable that we're defining now, is in last def, then we know it's time to delete. And what we'll delete is the instruction there. So just to illustrate what's going on here, in this case, we have something that looks like x equals 5, for example. And this is the instruction we're currently processing. And then the last definition for x is something like x equals 2, and that's the thing that happened earlier in the basic block, and that's the thing that we know we can delete. Regardless of whether we delete instructions, however, we also need to update our bookkeeping map. That is, we need to update last def, so we're also going to have to say that now, after doing that, that is like either deleting the instruction or not, we now know what the last definition of this instruction is, of this variable, rather. That's the current instruction. So now that we've defined this thing, this instruction is now a candidate for deletion because the variable has been defined but not used yet, and there may be more uses later in the function. Notice I wrote def here, but of course what I meant was dest. So this is pseudocode that implements our first sort of local optimization that has to reason about the actual order of instructions. This one, you will find, has a similar problem to the previous one, which is that it sort of peels away one level of dead code, but it makes sense to keep on doing that iteratively until we have pruned away chains of dead code. So to make this work in a real system, we'll want to take this entire program and wrap it in a big while loop that says like, while the basic block didn't change, and do this iteratively until convergence. But beyond that, we now have a more powerful dead code elimination pass that uses local analysis to complement the global analysis, the simple global analysis we saw in the previous pass. Pseudocode is all well and good, but now it's time to get to implementing. Please take the pseudocode you've written for these dead code elimination passes and code them up in, again, whatever language you like. You should implement both of the passes, and you should iterate them to convergence so that they are as powerful dead code elimination passes you can muster based on this framework. There's, of course, other ways to eliminate dead code you don't need to explore. Just take these two passes that we have designed so far and implement them in real code. I'm going to show you a pass that I have written that is available in open source, but you should absolutely not look at as part of the exercise of developing this algorithm yourself. And I'm going to show you how to run this on real code.
Okay, let's take a time for a break. Alex, do you also go through this course, or just came up randomly to the stream and don't understand what is happening? by mistake. I thought the 4 minutes left that I saw earlier was already a break. Okay, we'll just skip the break and we'll start from here. I know that it's pronounced like here, but I like to add a bit harder R to those words to sound a bit more different than usual English.
In the notes for this lesson, there are links to various test programs that you can run your dead code elimination pass on. I'm now going to show you how I run my implementation of the dead code elimination pass on some of those examples. Those examples happen to be under examples in this test directory, and then there's this TDC stands for trivial dead code elimination because there's much fancier dead code elimination passes that could possibly exist. And then one of the programs I've showed you is just called simple.bril in here. So you will recognize this from the handwritten notes from before. And all I would like to do is optimize this. But first of all, I think it'd be nice to start by just running this program. And the way you do that, of course, is with your old friend bril to JSON that takes this text format that's easy to write and look at and converts it to JSON, and then I can pipe that into the bril interpreter. You're familiar with this. One extra thing that I'll show you is that the bril interpreter has an extra flag called -p, which is for profile, which will run the program like normal, but also print out some very, very simple profiling information, in particular the total number of dynamic instructions executed. Here, 5. There are 5 instructions. They all ran exactly once. So that's 5 instruction executions. You can use this as kind of a very simple metric to see whether you are in fact optimizing programs by deleting instructions that actually would have been run otherwise. So the program, in some abstract model of computer performance, goes faster, whatever that means. So I'll show you what it looks like to run my pass. I have a program that's just called tdce.py, and if I run that and I pipe it back into bril to text, then I can see that this program is transformed, and I have successfully eliminated one instruction from this program. If I wanted to, I could just use the word count utility wc-l. If I count the lines in the original program, well, there are 7 lines, and if I now pipe this all the way through this pipeline and I pipe that through wc-l, then I can see that I've eliminated 1 line of code from this, but that's not as useful as knowing the dynamic instruction count. So instead, it makes sense to pipe this into the bril interpreter with the profiling flag. And there's 2 super important things here. One is that we get to the correct answer. That is the same answer as the unoptimized program. If you did an optimization that didn't do that, it wouldn't be a very good optimization no matter how fast it makes the program run. But also, it's nice to know that the total number of dynamic instructions executed went from 5 to 4. Of course, beyond this, you probably want to run your optimization on more complicated examples. And fortunately, there is a little mini benchmark suite that comes with bril that you extended last week as part of the first tasks for 6120. So for example, one of the benchmarks under here, there's a FizzBuzz benchmark. We can bril to JSON that benchmark and then pipe it into the interpreter, and it needs an argument. So here we'll give it, for example, 5, and it runs some things, it prints some stuff, it tells us how many instructions it executed. It'd be nice to know if our optimization has any effect on this. So I'll run my implementation of this thing. I'll run in more advanced mode just to see what happens. And I will pass it into the interpreter, and it tells us that we eliminated 4 whole dynamic instructions. Well, that's not a terribly large amount, but anyway, you can see that this optimized a somewhat more realish program than the tiny test examples that are just looking for correctness. Have fun. I encourage you to, for example, use Turnt to avoid typing out these very long command line invocations, and so you can have a nice pleasant workflow while you develop your first optimization that is hopefully the first in a long journey of very cool optimizations you will write during the course of 6120.
Okay, what I would like to do is to actually try to make it possible to run bril programs from my scheme code. So you don't need to write those long CLIs. Run bril. It will accept JSON string and will run it. How it will run? We have a bril. Let's fork. We have a TypeScript bril implementation. Now we need to somehow run it. For this we will be using Deno JavaScript runtime, and we have it defined in let's just use models CS6120 packages. Let's build it with store Deno and bound variable glibc. Okay, not a big deal. Search. Packages base. Okay, somehow managed to skip native inputs. Is it okay? Okay, we have our Deno. Store, define Deno bin, store Deno car, string append. By the way, could I build just build with store? I can, but it doesn't return, you know, the thing I need. But okay, we can do like this, and we got a Deno binary. Now I always have no clue which one is which. Okay, I need system, and I will just construct Deno Good, it was executed, but I need output. Pipe. Oof. How inconvenient it is to write this stuff. Let's try. Yes, process is pipe to it from it. For an output pipe, and what should I do with this thing? Okay, at least we got some result. And what it plans to receive? Pipeline comments, index. Funny. Do not exactly understand what is going on. Receive pipeline comments. Okay. Pipeline comments. How the heck we got this stuff? Probably we flashed input by the pipeline call. Okay, use models ICE9 where the receive is defined. ICE9 receive. Cool. Read line. Get string all. Nice. We finally got this thing. So I also need to package a repo. Package or not even package. We'll take get checkout, maybe not get checkout. I would like to have an origin. Geeks. Now we need, don't know, max xyz. Get the reference packages, public real. Now let's build it, and it should obtain the source code for us. Barrel. Actual hash. We have a checkout. Inside this checkout we have Barrel.ts. Okay. Barrel. Now what we want to do? We want to run string append define Barrel. Barrel interpreter will be string append Barrel Barrel.ts. To the car. Ay. Understandable. Barrel folder. Reload model. Cool. Barrel folder. Check out actually. Barrel. Oops. Of course. I had to specify something to barely. Okay, one more break. Working with external processes is pain. We need some library and convenience wrappers or something like this, because this one is horrible. Also restarting the REPL is a pain, because gigs for channels is implemented in a horrible way. Okay, won't be wasting time waiting until it finishes. Let's start to watch the second video.
In this video, we're going to kill 3 local optimization birds with a single stone. The idea is going to be to shift our perspective on how we look at basic blocks, so that several different forms of redundancy all become apparent at once and become easy to eliminate in a single pass. This technique is going to be called local value numbering. As you might guess, there is an equivalent called global value numbering that extends the same reasoning to work on entire functions. We're going to focus on single basic blocks for now, and then later you'll see how to extend this to deal with control flow graphs. To start off, I want to look at 3 different forms of redundancy that exist in programs, and I want to emphasize that each of these 3 things can be subject to optimization passes that remove them as their only purpose. That is, in some compilers courses, in some textbooks, you'll see each of these 3 things discussed as completely separate optimizations. And there are cases where it makes sense to think of them as totally separate optimizations. What we're going to do in this video, however, is try to see the underlying phenomenon that underpins all of them and does a pretty good job at resolving all of these forms of redundancy. And that's what local value numbering does. So let's look at these 3 programs. The first one demonstrates dead code elimination.
what is the predicate for understanding if something available on the port? Something like port readable. At least now we can kill stuff. My bad. I don't understand why why the fuck it reads anything if char already returns false? Am I stupid or what? This one should return an empty string because from already is false. Okay, it is return this one, do some magic tricks. Very funny. Okay. How the fuck is happening? Negated success. Okay. Unexpected end of input JSON. Because we closed two. Not a big deal. Sorry. Now we have a real program and SCM. Right, we have what the fuck? SCM to JSON. Very program. Nice, and two. having a hard time running a very simple program and sending the int to yesterday. What a beautiful Unix world. Nice. String int. Is it some kind of error? Oh, sorry. Sorry, bro. Cool. We somehow managed to run this pipe, which is awful, by the way. Just completely awful. Really been.
That is cases where there is code that has no effect, can't possibly have any effect in the output, and the optimization just consists of deleting the redundant instructions. The second one exhibits an optimization that is sometimes called copy propagation, which just where there is code that has no effect, can't possibly have any effect in the output, and the optimization just consists of deleting the redundant instructions. The second one exhibits an optimization that is sometimes called copy propagation, which just says that if you have several instructions, several computations that reuse the same original value, it is often easier to just use that value directly. So in this function, we might eliminate all of these instructions, and instead of using all those IDs, just print X instead. That optimization is sometimes called copy propagation. The third one, the third program here, demonstrates a different form of redundancy. This one, if you squint at it for a second, this is the long instruction-y way of saying A plus B times A plus B. And this represents an opportunity for what's called common subexpression elimination, where these things are the subexpressions that are common. That is, like, it's the same computation being done twice. And a better thing to do is just to do that addition once and then return the multiplication of that thing by itself. So we shouldn't need to do this sum2, but of course that variable is still referenced here. But if we were to just replace it with sum1, then we'd get the same answer. That's common subexpression elimination, sometimes just abbreviated to CSE. So my deep philosophical question for you is to ponder what these three examples, what these three different forms of redundancy all have in common. That is, what is the fundamental underlying phenomenon that is making these programs redundant? There is no right answer to this question. I, of course, have an answer in mind to this philosophical imponderable, but I'd like you to think for a little bit, just by yourself, about what is the common thread between these forms of redundancy. I'll tell you my answer in a second.
I would say the common thing about all those optimizations that they deal with the code, that either use already they compute already computed value, or they do a computation that is not used. I think it's generic enough to cover all of those optimizations.
The reason that these programs all have redundancy is because they say to compute things using the variables, whereas it is equivalent to just look at the underlying values being computed. And if you do that, then these forms of redundancy kind of automatically disappear. So let's look at these programs again. A value numbering approach to optimizing this program will realize that the same variable is being used for two different values and try to disambiguate those two things. And then we'll end up with a program where there's two separate values, one of which is clearly unused. This makes it easy to eliminate that unused variable and get us down to a program that just assigns to A once. Looking at this second example, the one with copy propagation, the philosophy of value numbering, that again is trying to disentangle the values from the variables, says that there's only a single value in this program, that is the constant 4, and it's being reused multiple times for multiple variables. And that's what looks like waste from a value numbering perspective. If we disentangle that single value from all those different variables, those other variables that can hold that value simply fall away, and we can see that the print statement should just be referring to the underlying value. Finally, let's look at the common subexpression elimination example. In this one, the value numbering philosophy says that there are two variables, sum1 and sum2, that hold the same value, that is a plus b. And of course, here we're getting into the tricky notion of how you define what a value even is. It's not just a constant. There's something underlying going on here about reflecting what computation is being reflected by the variable. But if you accept some careful definition of what a value is, then the value numbering optimization is going to look at this program and realize that the same value is being stored in two different variables, and that's redundant. And so in the computations that consume those variables, it suffices to just use a single one, and that will reduce and eliminate the redundancy. So let's see how the value numbering approach actually works. I'm going to give this idea to you at a very high level, and then we're going to walk through an example to see how it plays out. Finally, I'm going to leave it to you to develop the actual pseudocode and implement the algorithm. But the idea behind the value numbering as an optimization really revolves around one big data structure that we'll see here. There is a table, and as this is where the name comes from, that's going to assign a bunch of numbers in the left-hand column, and by this I mean like literal, actual, natural numbers, assigned to the values being computed. Values you can think of as expressions. I'll talk about the representation of values in a moment, but we're also going to maintain, for every value, a canonical home for where that value is being stored. So the very high-level idea is that we will try to disentangle a notion of values that is sort of expressions that are being computed, and also keep track of one place and one place only where that value is being stored. So for example, if we end up using the same value in two different locations, even if they're stored superficially in two completely different variables, this approach will be able to look through it and say, no, that's actually the same underlying value. And instead of computing it again, we can just look at the canonical variable that's storing that thing already and just use that variable. One of the important things here is how to represent the computations, that is the expressions, the values that are being numbered. And as this table that I'm showing you indicates, we'll represent that in this kind of like funky form that refers to other rows in the table. So here we have this like number 1 plus number 1 expression. What that actually means is that this is the addition of value number 1, which is currently stored in variable x, to value number 1. So we're not going to, when we build up these values, we're going to be storing them as using these actual numbers that refer to rows in the table. So every expression that shows up in this column of the table will be referring to values by their numbers rather than by their variables. And this is sort of completes the disentanglement from between variables and the values that they're stored in. By having self-references back to this table to say like, well, this is one big value that's computed out of several smaller values, then we can live fully in the abstract realm of computed values and maintain a mapping to where those values are stored in variables. This all sounds fairly abstract, and I swear this is going to get more concrete in a second when we go through an example. However, there's one more piece to the data structure here. This is sort of the main table data structure, but there's one other thing that the algorithm is going to need, which is we're going to step through the basic block, instruction by instruction, keeping track of kind of the imaginary environment that would be happening if we were actually executing the block. So it's going to be like executing the program. We'll step through and sort of keep track of what every variable holds. But instead of like in a normal interpreter where every variable will hold like an actual concrete value, like 5, they'll hold this notion of a value that is one of these expressions. So this cloud I'm showing off to the left-hand side here is going to say that we'll have an environment. So after we execute a expression that assigns, after we execute a statement that assigns into the variable a, we'll have this environment that says that, okay, a now currently holds a value number 2. So it's going to work exactly like an interpreter, but instead of holding actual concrete runtime values here will just be the numbers, that is like the indices into this table. And this way we'll be able to keep track of a model of what computations go on in a basic block, just like an interpreter does, but statically, that is without actually knowing what the inputs are. I hope you've had a moment to ingest that very high-level description. We're now going to go through a concrete example that will hopefully make these things a little bit more clear. And this is a pretty tricky and abstract way of thinking. So if you have any questions at all, I encourage you to either bring them up on the next Zoom iteration of this class or to ask questions in Zulip. You really, really got to ask questions if you have them, because I know this is not easy to understand. So we're going to start out with this program on the right-hand side. So this is the common subexpression elimination example, and we're going to start executing this program in a LVN style. That is, instead of actually interpreting it, we're going to maintain one of these tables. So I'm going to start by like drawing the main data structure we have, which is this numbered table. It's going to keep track of all the values computed in the program. So there's that value table. That's where we're going to put these funky expressions that refer to other rows in the table. And then we'll also keep track of the current canonical home for that value in this variable column. And then off to the side, we'll have this fuzzy cloud, which is the current environment, which reflects the current state of all of the variables in the program. Everything starts out empty. Of course, we're at the very beginning of the program, and there's nothing in the environment, and there's nothing in the table because nothing's...
Do we create a row in the table for values which doesn't have variable name yet? For example, for const for, okay, it has a variable name actually just after this line, but do we put const for here directly into value?
It's been computed yet. In the next frame of this animation, we're going to advance past the first two instructions, these constant assignments to A and B, and see how that affects the environment and the main data structure for the LVN pass. So at this point, that is like right after the A and B assignments, we need the same table with number, value, and variable. What this algorithm is going to do is insert values for A and B that are going to be pointed to by this cloud off to the left. Remember, that's the environment that keeps track of the current values of all the variables. And every time you sort of manufacture a new value that like hasn't ever existed before, you need to insert a new row in the table. So these are going to get the first two numbers. We'll call them 1 and 2. The value here, you can imagine that you have a way of expressing what constants are. Let's just say that, yeah, the value here is going to be const 4, and this one's const 2. Those have never shown up anywhere else in the program. The canonical home for this computation is A. That is, we will associate, whenever we compute something, we'll say, if it's never been computed before, we'll say that the canonical home for that, the variable associated with it, is the one where we've already stored it. Great, so that's the first step. That's not so hard. Okay, so the next step is to interpret this add instruction that stores in sum1. To make this kind of animate, I'm going to copy and paste our data structures and just extend them. Now at this point, that is between the sum1 and sum2 expressions, both adds. To execute this instruction, we are computing something that has never been computed before. And the way that you confirm that is by looking through the value table, just scanning over everything in the value table and seeing whether we have computed anything that looks like this. To do that, we're going to have to come up with a representation for what the new computation is that we'll insert into the table. So we have like const 4 and const 2 for the actual constants. What are we going to do for adds? The way to do this is you need a representation that you can easily compare for uniqueness. And
so we have value A, value 1 plus value B, and it will be value for the variable sum1, and we'll have number 3.
And the way we will do that is by building up tuples. So the representation concretely and computationally when you're implementing LVN is to use some sort of a tuple. This is sort of like hash consing if you've ever done that in functional programming. This tuple is going to include a symbol to say that what this is an add, and it has 2 arguments. And those arguments are going to refer to other rows in the LVN table. That is, they're just going to be the numbers indicating other values. So the way this works is we're going to fill up these arguments by saying, okay, so what is the current number associated with the variable a? We need to look at the cloud to see the current value of a is refers to the row 1. So we'll insert, so the value number for this argument is 1. And we'll do the same thing for b, look it up in the current cloud, the current environment, its number is 2. So the new value being computed can be represented by this tuple, add 1, 2. So LVN looks through the value column of the table and sees, is there anyone else who has ever computed add 1, 2 ever before? And if the answer is no, we are going to insert it into the table to say that we have now computed it, and anyone who computes it in the future can just reuse this. So I'll just write that value here in the table. Add number 1, number 2, which is the tuple representation of the value we have just computed. We will now need to sort of clean up the rest of our bookkeeping, which is to say that this gets its own value number, it's 3. It gets a canonical home, which is sum1. And then we need to update the cloud, that is the current environment, to say that sum1 points to row 3. Okay, so the next step is we need to do something very similar for sum2. So I'm going to, again, copy and paste these data structures that we have just finished computing for this step, and we'll see how they animate when we apply them to the sum2 instruction. So the way LVN works is it's going to look at the expression being computed here, and so it's going to construct one of these value tuples to indicate what this new instruction does. So again, this is going to say, well, that's an add, and it's got 2 arguments. And again, it's going to look at A, look in the cloud, find out that's number 1, still. It's going to look at B, look in the cloud, find out that's number 2, still. And now we have the value, the value tuple that is being computed by this new instruction. LVN likes reducing redundancy, so it's going to look at this tuple and look through the value column to see, has this ever been computed before? And the answer this time, for the first time, is yes. There is already something in the value table that looks exactly like this, and so there's an opportunity to reduce redundancy. So instead of adding a new value to the value table, like we've done every single time before, we will do nothing. We'll put nothing new in there, and we'll just say, great, we now have sum2 in the cloud, that is like the current state of what all the variables currently point to. That now points to the same thing. That is, we don't need a new row in the table. This row suffices perfectly fine to represent the value of sum2 as well. Crucially, we don't need to update anything about this variable associated with the value. That is, the canonical home, the original place from which you can get this value, is still here in sum1. So this indirectly, if you kind of read the arrows going here, this is now saying that sum2 holds the value number 3, which is this thing, but that doesn't really matter. What really matters is that it's the same thing as sum1.
So we basically can update this expression. We can update this expression to sum2 equal to sum1, and that's it. We will avoid recomputation of the same value we already have, and we'll simplify the program a bit.
So that later on, computations, in fact, in the very next instruction.
And the best part about it is that we have a very small language which have a very few operations with a very clean semantic. That means that our add function or mul function won't produce any side effects, won't print to std out, won't access network or whatever. And we can do such optimizations without worrying that we lose some properties of the program or some functionality.
Computations that use sum2 don't need to literally use sum2. In fact, they can look somewhere else for the same value. Great, let's now do the next instruction. That is the multiply of sum1 and sum2. I will copy and paste these data structures again and move them right after prod to see what happens there. The algorithm for constructing the value is, again, just as it was before. That is, this time we will use mul as the opcode, and we're going to need the values associated with its arguments. So here, the first argument is sum1. LVN goes to the cloud, the current environment. It says that sum1 is value number 3. And then it goes back to the second argument. It sees that sum2 goes to the cloud. It sees that that is associated also with number 3. So it reconstructs this as multiply of 3 and 3. So finally, it can put into the table a new thing that has never been computed before, this mul number 3, number 3. That gets value number 4, and that gets put into the prod. And the variable that is the canonical home for this multiplication is still prod. So we adjusted by virtue of having already figured out that sum2 holds the same value as sum1, we have now adjusted the value tuple that we have computed for prod. There's one last step here, which is to go through with the print instruction, but it's not all that interesting because it doesn't actually compute anything. It's only going to sort of look up the value that's being used for print, find its canonical home, and use that variable. So that's the entire process for scanning through a basic block and instruction by instruction, building up this LVN data structure, associating values with variables and disentangling. So that's the entire process for scanning through a basic block instruction by instruction and building up this LVN data structure, disentangling the values from the variables and assigning numbers to all of the values in order to do that. There's one thing that we haven't done though, which is to actually optimize the program. I've only shown you building up the data structure. I'm going to rewind a bit and go back to the first frame and show you what happens kind of alongside as we transform the program. So you shouldn't think of this as a second pass, really. This is something you can do on the fly while building up the data structure to automatically reduce the redundancy in the program. The basic idea is that every time you finish maintaining the data structure, you reconstruct the instruction we just processed according to the value tuple in the table. This means that we eliminate the old instruction, which is based on the way that the original programmer happened to associate the values with variable names, and reconstruct the same computation based on the values themselves, kind of ignoring the variable names. The way this will look is that, for example, when we have finished processing this sum1 instruction, we will cross it out and reconstruct it from scratch based on the table and the value the value tuple we have just created. So this works by saying, okay, well, this needs to store into sum1. We'll leave that the same, sum1 colon int. We're going to store something in there. And then we will look at the value tuple we have just constructed for this. So that's this tuple add number 1, number 2. And we'll say, great, I know how to do that. I will create an add instruction to reflect the operation being performed. And I'm going to come up with the 2 arguments to add to put in here. To do that, I will look at entry number 1 in the table and its canonical home, which is A. So this is going to be add A. I'm going to do it again. I'm going to look at entry number 2 and its canonical home, which is variable B. Surprising absolutely nobody, we have reconstructed an instruction that looks exactly the same as the old instruction. And that's what this algorithm must do, is reconstruct instructions from scratch, even if they look identical to the old one. It's not any surprise here because this is the first time this value has ever been computed, so we need it to be computed somewhere. It just so happens that it will be computed right here and then used to eliminate redundancy later on. Let's look at what happens when we follow this reconstruction algorithm for sum2 instead of sum1. So we'll cross out the old instruction and we'll again say, okay, we need to assign to the same variable. It's going to be sum1 colon int. But this time, when we look up the value associated with add AB, we found it in the table. That is, we didn't need to insert a new value in the table. So that computation already had a canonical home, which is sum1. When that happens, instead of reconstructing the add operation from scratch, we can just say, now you are an identity operation that now contains exactly the same thing as the canonical home for this computation. So this will just be ID sum1. So in reconstructing this instruction, we get rid of the add altogether and replace it with just a copy. Next, let's look at the prod instruction. We'll follow a similar algorithm, which involves crossing out this thing and saying, okay, great, I'll replace you with a new prod colon int equals something, and we'll figure out what that is. This computation was, this value was inserted into the table. That is, it got its own new row, which means we don't get to play the ID trick to reuse an existing variable, but instead we will have to do a mul thing, and we will insert the arguments. To do that, we will look at the value tuple, and we'll see that it uses number 3 and then number 3 again. So looking at the number 3 row, we see that the canonical home is sum1. So we'll multiply sum1 by sum1. So that's not quite the same as the original instruction. We've reconstructed a new instruction that means exactly the same thing, but instead of using sum2 as a second argument, we get to use sum1, which is fantastic. We have now eliminated the need for sum1 altogether.
For sum2. Yeah, cool. Now, after we did LVN, am I called correctly? Local value numbering. Yes, after we did LVN, and we rewrote. After we did LVN and we rewrote all the instruction into new form, we now have redundant instructions that was previously used, but right now they don't make any sense, because right now our prod value will be multiplication of sum1 and sum1, and sum2 is unused variable now. So we can do LVN and after that DCE, that code elimination, and get an optimized program that don't do unnecessary computations, which is cool, which is really cool. It looks very simple and clean and understandable, but with the amount of optimizations added to the compiler, the complexity of the compiler like blows up. You can see how one optimization affects the quality of another optimization, the scope of another optimization. So depending on the order of optimizations, we get different final results, and it remind me one project that I try to remember name. NanoPass compiler. Is not updated for some time, but I guess there was another project based on NanoPass compiler. Parser, prefix, matcher. The magic of hygienic macros. I'm curious if there are some optimizations somewhere. Okay.
We follow this thing through to its logical conclusion. We will also have to reconstruct this print to see where its value should actually come from, but it will just be reconstructed as print prod because the canonical home of value number 4 is in the variable prod. We'll end up with a basic block that has been transformed to replace prod with two different references to sum1. Sum2 is now just a copy of sum1, and that instruction is now dead. So we've optimized a couple of different things at once, and all that needs to be done now is to run a trivial dead code elimination pass, like the one from the previous video, to just remove the assignment to sum2, which is now completely dead and never used anywhere in the entire function. That simple cleanup pass will remove this instruction and let us reassociate with sum1. So in combination with that very, very simple dead code elimination pass, we've gotten the full effect of a common subexpression elimination pass as well, through this shift in perspective from thinking about variables exclusively to thinking about the values that underpin the computation. By reconstructing these instructions, we got rid of the redundancy and made it really easy to remove dead code. That's the basic algorithm for doing local value numbering. I promised you before that local value numbering is kind of this all-encompassing way of looking at the world that makes a lot of optimizations happen automatically. Really, it's a sort of a framework for implementing different optimizations as little tweaks to the basic LVN algorithm.
I think we will do a long break, and after that we'll finish watching collection, and maybe, if I have time and desire, of course I have time, we all have time, if I have power and desire to do something, I will write both that code elimination and local value numbering, and we'll try a few programs and see how much instructions will be eliminated by it, by optimizations, I mean. Okay, I guess let's finish watching the lecture. We already know what to do and how to do, but let's watch the lecture first.
Next, we're going to walk through a few of the extensions you can make on top of the basic algorithm in order to make other forms of redundancy go away. In each case, I'm going to show you a original code on the left-hand side and new code on the right-hand side that we can hope to produce. So here is the first optimization that we kind of get for free out of the basic LVN algorithm, and that's common subexpression elimination, a behavior like a traditional CSE optimization, which says that you can delete this sum2 instruction, and you can replace this reference to sum2 with a new reference to sum1, which is a canonical home. And I'm kind of alighting the fact that we need to do a really, really simple dead code elimination that we saw in the previous video in order to just to clean up the dead instruction we've just created. But in any case, the optimization as we implemented it so far can perform this type of optimization and get rid of the redundancy. Here's a different form of optimization, copy propagation. That is, getting rid of these chains of IDs that should all result in the same value. Let's get rid of all those instructions, and in fact, just replace them with IDs. Now I'm not doing the automatic dead code elimination, the trivial dead code elimination here, but we can still just use X directly. The algorithms I showed you so far doesn't actually accomplish this. The key to making it work is understanding something about the underlying semantics of the language. The basic framework I've shown you so far doesn't say anything about what actual instructions do, what the meaning of add is, what the meaning of multiply is. None of that matters for the basic LVN framework. This tweak to it, however, does. The instruction it needs to know about, the semantics it needs to understand, is the ID instruction. It needs to know that ID takes a value and produces exactly the same value. By adding that understanding, that level of semantic awareness of the underlying language to LVN, we get this optimization. The tweak to the algorithm is that when you construct a value that looks like this, that is, whenever you see a value that says ID and then has an argument, you just consider that to be exactly equal to number 1. So when you look in that value table of the column for instances of this value, you consider anything that you consider this to be identical to value number 1. This means that we get to replace all of these instructions with copies not of the previous variable. Without this awareness, we need to just sort of assume that ID can do anything, and we just get to refer to the underlying value. So this is just sort of a small local tweak that you can make to the LVN algorithm that introduces some awareness of the semantics of the Brill language that makes a totally different kind of optimization happen more or less automatically. Next, let's look at a different form of optimization. So this is going to be an enhancement of the common subexpression elimination behavior. As you know, add AB should be in any reasonable language the same as add BA, of course, if we're talking about integers. So this instruction should do the same thing as this instruction. That's not, of course, automatically true. The basic LVN framework has no idea that this is true of the add instruction. So just like in the ID case, if we just teach it a tiny bit about the semantics of Brill, about individual instructions in Brill, we can make this different optimizations happen. In particular, what will happen here is that we will get to apply the same CSE logic as we did when we had add AB twice, and we'll get to replace sum2 with sum1, and then finally DCE away the dead store to sum2. I would now like you to think about exactly where you would need to change the LVN algorithm in order to get this behavior. That is, in order to transform this program into this program by just running the LVN algorithm. Where is that one small change where we need to introduce awareness of what the add instruction actually means? Think about it and come up with your answer before you unpause the video.
So basically, when we construct a value that produced by the expression, we can just order all the arguments to add function. We construct a tuple add value 1, value 2, value 3, and if you know that add, mul, or whatever operation is commutative, if the operation is commutative, we can reorder the operands for this operation. And this way, if we always sort in the same order all of the operands, we now can compare with already pre-existing values, because they will be also ordered by some principle, and will have probably the same value, the resulting value.
Here's how I think you should do it. There are many ways to do it, but I think that you should implement a canonicalization pass on values. That is, as soon as you construct a tuple like add AB, that is, it will actually look like add number 1, number 2, for example, you check for commutative operators, and whenever you do that, you canonicalize them so that the value numbers are always non-decreasing. So if you have add number 2, number 1, you canonicalize that to add number 1, number 2, and then when you're scanning through your table, you'll find an exact match on the canonicalized form of the value. That would work for this commutativity optimization. Here's yet another one, constant propagation. In this version, it's just like the copy propagation, except we want to replace IDs with something even simpler, the const instruction. So this means that if you ID through a bunch of time, the same underlying constant 4, we can replace that not just with IDs, but we can replace those things with const instructions. You can think now about where you would need to change the LVN algorithm to teach it the semantics of const to make this work.
But don't understand yet why it's useful. It definitely can be useful somewhere, but not sure where. Like, we already got this optimization that instead of print copy 3, we can use print x.
I'm not going to reveal the full answer this time, but I think this has to do with where you reconstruct instructions in the algorithm. Okay, so here's one final one. This sort of demonstrates the full unbridled power of LVN. It should be possible to take this entire program, because it starts out with constants, 4 and 2, it does like a bunch of sums, does some products and stuff, and finally prints things. I think we should be able to turn this into something that just computes an actual number. This optimization is outside of the LVN context called constant folding, because it's not just propagating constants, it's folding them through operations that act on constants. So if you know you have a constant, and you do an operation to them, you can compute at compile time that constant. And that's pretty cool.
Okay, now it's clear why we would like to propagate constants to do compile time computations.
Because it lets you get rid of a whole bunch of computation that would otherwise be done at runtime and basically simulate the same effects at compile time, replacing the whole thing with a constant expression. My implementation of LVN, with all of its power combined, is able to, in fact, reduce this entire big program to this tiny one that just uses a single constant, simulating the effects of the program at runtime. I'll let you think offline about where exactly you would need to make tweaks to the LVN algorithm in order to make this whole thing work. I also want to emphasize that we're talking, again, the L in LVN is for local value numbering, which means that this thing only works because we're doing all this computation within a single basic block. In my implementation, for example, if you were to jump to a label that's right here, it would totally break because it would be able to optimize some things around in here, but it wouldn't get to know that the inputs A and B are constants. It only looks at a single basic block at a time. So those are the myriad ways that it's possible to customize the basic LVN framework with little tweaks, introducing the semantics of the underlying language to make more optimizations fall out. There are many others. We won't discuss them here. Where we're heading is to do an actual implementation of LVN for Brill. That's your main task for this week. I have to emphasize that this is that this may seem easier than it actually is. There's a lot of fiddly details you're going to have to get right in order to get an implementation that is both correct and actually optimizes the programs. All of these extensions to LVN are bonus for this week's task. You don't actually have to do them. Just getting the basic framework is the task that you have to do. The next step that we're going to do here, however, is go over the pseudocode for taking these vague ideas and these pictures scrolling around on an iPad screen and turning them slightly closer to an actual algorithm. I would really like you now to pause this video and take some time, not just like a couple of minutes to think about it, but try actually sketching out the entire pseudocode for how to run this LVN algorithm. Think carefully about what the data structures are going to have to look like. Again, it's pseudocode, so you don't have to think about how to implement those data structures, but think about what has to map to what, and write the for loops and the assignments and stuff, indicating exactly where you're going to replace instructions and where you're going to insert things into the data structures, thinking through the entire pseudocode for this. I'll show you my pseudocode and talk through it, and then it's going to be on you to implement that. Okay, here's my pseudocode. It starts out with the
I don't know if I want to watch beforehand his implementation. I want to implement this function correctly so it can produce me both error, out, and ideally handling the case where the program crashed or just hanging. But okay, we probably can always give it a proper input so it can proceed somehow or fail quickly. Moreover, the interpreter probably quite good, so it won't fail unexpectedly, at least too often. Okay, let's finish watching this thing.
Initialization of the data structures, which you'll recognize from the terribly drawn cartoons above. The first one is the table, which that's the thing that looks like the table above. I phrase it slightly differently here as being a numbered mapping from values to canonical variables, but really it's a sort of three-way relation that includes the number, the value, and the canonical variable, the canonical home of that value. I'll be sort of using it as a map that's keyed by the values. Then there's the var to num map, which you can think of as the cloud we were using before. That's the environment that keeps track of the current values associated with every variable that has been assigned to so far during our scan. And here's the scan. We're going to just iterate through every step every instruction in the block. The first thing to note about actual concrete implementation of this is that you're going to need some representation for values. That is the value thing here that I've been sort of referring to as a tuple. The main reason I keep on calling it a tuple is because we need to be able to do equality comparisons. We need to be able to look things up in the table table here indexed by this value, which means we need to be able to compare things. We need to construct one of these tuples and check whether there's an existing tuple that's the same thing. Whatever language you're using to implement LVN, it must have equality defined for the type that you're using to represent values. That is, you have to be able to do in kind of Java terms, like dot equals instead of double equals. That is to say that like we need to compare them for equality and not for identity. I'm going to skip over the big if in the middle of this loop and go to the very end to show what happens regardless of whether something is in the table or not. When we do this in table, that's where we're going to use that equality on values to look things up, to decide like whether this already exists or not. We're going to do some stuff, but eventually we're going to maintain the cloud. That is, we will add like whatever the destination of this new instruction is, that like new variable x is now going to point to some row in the table. That table entry num is going to be decided differently for the two branches, but regardless, at the very end, we're going to need to update the cloud to point to have the variable be tracked in the current environment. Okay, so let's now look at the two possibilities. The first possibility is that the value already exists, in which case we have found some redundancy, and what we're going to need to do is replace the instruction with something that eliminates that redundancy. And what I mean by with a copy of the variable is that I mean that you should say like the destination is like ID of var, where var is the canonical home that we got out of the table. So this case is fairly straightforward. The other one is slightly more complicated, not that much more complicated. So this is a case where we have a newly computed value that has never existed before, and we just need to do some bookkeeping. So the way this works is we will get a new number that is like the next row in the table, if you will. And I'm going to skip over this this nastiness in the middle, which is a complicated, unfortunate thing we'll deal with in a moment, and just talk about the bookkeeping we do with that number. We need to update the table to with that new number to track the canonical home of the value. So that means add a new entry to the bottom of the table that has like the new number, the newly computed value, and the new destination that is now the canonical home of that value in case it's ever being used again in the future. We will then update the actual instruction. So we can, this is that reconstruction step that says that we will use values from the table instead of the original variables. That's actually fairly straightforward. It's just that you have to go through all of the arguments and replace their old variable names with the canonical variable names for those values. Okay, finally, I promised we'd come back to this nasty bit in the middle, which deals with kind of an unfortunate circumstance of the LVN situation. In LVN, remember the philosophy is we're trying to disentangle the notion of values, that is things being computed, from variables, that is where they're being stored. And there is one situation where that's particularly inconvenient when it comes to the realization of actual variable names. So far, we have conveniently been able to just leave all the destination variables named the same thing that they were before. Here's a circumstance where that is leaving all the variable names the same, becomes a problem. Say that you do x equals some computation, like let's say x equals a plus b, I don't know, use x for a while, and eventually you reassign x to something else, and then do some more computation, and then eventually you do another copy of the same computation. That is, you compute the same value, a plus b, and a and b have not changed so far. If that's the case, then LVN will want to, in fact, it should be able to eliminate the redundancy in y and just reuse the computation we already have. However, this is obviously a problem because x doesn't hold that value anymore. Through the unfortunate conflation of values and variables, we don't have the original value that we thought we had. So doing this replacement would be unsafe. What we actually need to do is to, let's call it x prime or something, to rename this to a different variable so we still have it around in case it gets used in the future. One way to do this, which would be very ugly, but also very easy, would be every time you reconstruct an instruction, you make a completely new variable name for it. That is like, just call it like variable 1, variable 2, variable 3. And this would totally work because it would sort of, it would complete the disassociation between the old crappy variable names of the past and replace them all with variable names that just represent the nice clean world of value numbers of the future. However, that's not really all that friendly. It is a little bit nicer to sort of be lazy about it and reuse the old variable names when possible and only do renaming when necessary. So we're going to take that approach. That is, we will we'll like rename things as x prime only opportunistically, only when we have to, instead of renaming all the variables eagerly. So that's what this pseudocode does. It does a slightly tricky thing to say if the instruction will ever be overwritten later. That is, if the, I guess that should probably actually say, if the inster.dest will ever be overwritten. That is, if there's any other instruction later in the basic block that will ever write to the same variable, then let's do some renaming. Otherwise, just keep the same old name for sanity's sake, so you don't lose track of what variables came from and went to where. So in that case, we will just you can just construct a new fresh variable name and say that's the destination for this instruction. And when you reconstruct the instruction, insert it back into the program, we'll use that new variable name. And also, when we set the canonical home for the newly computed value, we will say that this is now x prime instead of x, so that future uses of that value will go to the right variable. So that's the entire pseudocode for LVN. It's got some intricacies to it. That variable name thing is just kind of an unfortunate, weird consequence of the fact that variables can be reused, whereas values are kind of forever. However, the overall idea is fairly straightforward. Making it work and making it work without bugs is another story, and that is your task for this week. Good luck translating the pseudocode that you now understand in depth into real code and making it work on real programs.
Okay. Let's try to implement our function. It has almost everything that we need except this one. Okay, we don't need this. Great. The only last thing that is left to do is to actually, instead of taking this value, obtain this value from string. Input port. Okay, error to port. We put it to pipe. After that we close the pipe and read from the beginning of this pipe. Okay, and the result open input pipe. Output. That's of course nice, but how to open read write port? Okay, so that means we open input output, and before getting the result we need to SCM to JSON real program port. Wait a second. Something went wrong. I guess it will be the last working block, and after that we will finish stream. So let's try to focus on providing infrastructure for running things. How was the things in Abu Dhabi? Good. Most of the time I sit in front of my computer. I have a few workouts in a week, like 3 workouts. I go to Muay Thai gym like nearby, 10 minutes away from home, and usually on weekends I go to the rocks in Ras Al Khaimah Emirate, and they're surprisingly good. They're like there are a few places where you can climb. One of them is very popular, called Stardust. It has, I don't know, 50, maybe 60 routes, like quite a lot. It's 8 sectors, and each sector contain at least like 4 routes, I guess. What else? There like another place where we went the last weekend, which has like maybe 15 routes, but it has like some good grades, some very interesting stuff. It's a bit like dusty, and you know, you can break the holes and all that stuff, but overall it's almost always much better to go to the rocks rather than sitting at home under the conditioner. Okay, now I think we need to come back to our code and actually implement some stuff. We have the sample Brill program. We have SCM to JSON function, which can print this program to the port. By the way, let's take a look that it produces the same output. Functions, instructions, name. Yeah, it seems like an equivalent. Value type, operation, destination, operation, labels, label. Yeah, looks pretty good. Now the question is how to run this program. Sorry. Not really sorry. If we have this port, we can write to it, right? Let's let's try this approach with error to port open output pipe. I am interested what happens if we do open output pipe. Does this stuff related to stdr will still work? Parent and child are writing. Okay, I think we somehow getting to this problem. so frustrating to write a useful code in scheme that interacts with external processes. I mean, I understand that it's not the easiest task usually, like in general. Spawning processes, the same for Python and all other languages. But come on, it should be like a very straightforward option to run a fucking process, to feed input to it and to read the output from it. What? Okay. And we hanged our rebel. Tell me, what am I doing wrong here? We have a program, we have a port, and we write to this port. After we finished, we go and read from this port. Do we want to fucking takes ages to restart the process. Why, people? Why you implemented this in so fucking inefficient way? It completely ruins the user experience. Waiting 5 minutes until nothing is rebuilt, because it's absolutely the same channels from absolutely the same source code. Okay, I simplified it as much as possible. All right. Maybe we can even see the result. Not very clear. Why the file is still empty? Okay, let's uncomment those things. Cool, it works. Probably here we will get our deadlock. Very nice, very convenient. Now, what can we do? non-blocking IO. This is a monkey way to test hypothesis. I just throw random pieces of code and see if something of it works. The winter storm in New York. I didn't see snow for a few years, I guess. Since the time I left home. I would like to ski actually, to snowboard. And maybe to ski. I would like to learn skiing. Reading the chat and focusing, but we still don't have anything to do right now because we wait until our REPL is restarted, which is stupid. We need to fix this thing. It's not the way it should work. Okay, we are not that frustrated. I can be focused for 15 seconds. Dubai definitely has indoor ski resort, but I bet it insanely pricey, and also I don't have my snowboard with me, and of course I don't want to spend like tons of money doing very questionable skiing in a very small resort. I mean, even if it's a few hundreds meters long, it's still probably not the nicest place to ride. I like the mountains and forests. It's, exciting. You feel some kind of freedom. It's cool to navigate between the trees and try not to crash into it. It's cool to see the mountains around, but being in even big house, like covered with the snow inside, is not the same feeling. It's still skiing, it's still snowboarding. You can probably even have a good park in it, but I don't know. I'm not a big fan of indoor skiing. I did it once, I guess, in Moscow. Okay, let's try our hypothesis and see if it works. And it probably doesn't. Okay. First thing that we really need to fix, a channel build system. We don't actually need to fix the build system itself, because I don't even want to watch its implementation. We can just write a different function which will take all the channels and will create a package out of them just with the source code of them, and it should be enough. I think it should be enough. Right, we will change it to trivial build system and we'll do something with it, or Guile build system, and somehow we will fix it. Okay, I don't want to do it on the stream because I don't want to have a pressure and being frustrated even more. So I will do it after the stream. You should live in Switzerland. Yeah, that's a great idea. I agree. Can I have like a Switzerland citizenship, please? I mean, I would like to live in Switzerland for real, because it's like really beautiful country in terms of the nature. I've been in it just like for half a day, I guess. And I was already excited. We were traveling from Switzerland to Chamonix by car, and from Chamonix back to Switzerland, and spent some time in Geneva. And you know, it's so cool, like even in the summer, going by car through the whole country, it's very beautiful. And even the city itself have insanely clear water in the river that goes through the city. You can see the bottom of the river because the water is completely transparent, or very transparent. The lake itself is also quite good, quite nice. I didn't swim in it, and I don't know how good the water quality in it, but from the distance it looks very pretty. But the probably most prettiest part about Switzerland is that they have a lot of mountains. They have ski resorts, and they have via ferratas, so you can take a harness and go for a hike in the mountains, which will be relatively safe because you are connected to the metal cable with your I don't know how called this device, which absorbs the impact from the fall, but you have a harness, this device, and you connect to a cable, and you do like a beautiful hike in the Switzerland mountains. That's like insanely great. Maybe somebody who will be watching this stream afterwards and accidentally get to the end of the stream and work at ETH at some lab that do PLT will invite me to do PhD in ETH Zurich or Lausanne University or whatever, or some cool university that do PLT. Would be great. I lived in Geneva for an year, and it's great, but I thought that even senior engineer salary is not enough for that cost of living. Yeah, probably Switzerland is quite expensive. And living in main cities like Zurich or Geneva with usual engineer salary probably will be like from salary to salary and not very comfortable. But overall, the country is great. I need to figure out the way to get enough for living in it and to have a citizenship, or at least permit to live in it. Would be cool. At least for a few years. I guess Switzerland is relatively small, so you can spend like a few years and go to a lot of places. And you can watch the primary places and visit most interesting ski resorts and mountains through the course of a few years, and after that you can go further to a different spot, or maybe stay for a longer time. Just enroll in some university. Yes, probably it is an option. It is an option. Still don't know how I feel about it. It's a lot of, work to enroll to it. You need to translate a lot of documents, and probably you need to pass some TOEFL, IELTS or something like this. Work at Google and be transferred to Zurich. That's also an option. Actually, I was considering all those options already. I don't see like the one which will be relatively smooth. So I would like to keep working in the way I work. I would like to keep contributing to open source, keep developing IDE and distribution, and gradually find a way to come to Switzerland and to do studies and work here. Enrolling to some university or to Google is too direct approach. It should be fancier, because it's much more satisfying when it happens like almost on its own, when you don't like spend time directly trying to get to the Switzerland or trying to get to the some exact university. It's much more funnier when you do some stuff that you are genuinely interested in, and because of you doing the stuff and you progressing in it, something happens, and you get invited to the university or to the company or whatever. Sounds much more fun, but probably much harder. Okay, I guess I will take another break, and we'll try to rewrite this very unfortunately slow function for producing a package, or I would even say this slow package which get computed for so long time, but I will do it out of the stream. Thank you everyone who joined. Thank you, Alex, for a very nice chat. It was a pleasure to talk with you. I hope you enjoyed, and I will see you in a bit. Bye.